Okay, team, at this time we're going to review our airflow and duct design module 3 and 4 today. And so this is a recorded session. So if you were on the recorded session, by all means, just know that we do record these sessions if you happen to be participating today. But today is a recorded session, module number 3 and 4, airflow and duct design. So we'd like to welcome everyone to the program today. We're going to be learning about basic airflow and duct design. And some of the subjects we're going to be talking about today will include the following: building a typical duct system, supply and return, and also using the factory airflow charts and external static pressure, also called ESP, to find airflow for furnaces and those related products. So at this time, we're going to be practicing duct design based on velocity recommendations as the main consideration. Now, Manual D, a quote right out of Manual D, Chapter 3, says as follows, that there are two sizes associated with every duct section: the size that satisfies the airflow requirement and the size that satisfies the velocity limit. The final design is always based on the larger of these two sizes. Now, we know from building duct systems that typically, if you use the velocity method, this is going to give you a slightly larger duct. And even though Manual D does allow, as a matter of fact, it actually lays out the process for building a duct system on what we call static pressure, or more specifically, total equivalent loss method. That method is based on static pressure. And but what we're supposed to do if we build a duct system with that method, we're supposed to go back and make sure that we do not exceed the velocity requirement set forth in Manual D for each section of duct. So the method we're going to be using today is we're going to be going straight to the velocity method, or the velocity limit, or the velocity recommendations set forth in Manual D on our duct calculator. And then we'll choose that size. In addition, we'd like to please note that all duct runs or takeoffs should be equipped with a manual damper or with a damper for final air balance. So this time, let's go ahead and talk about building a typical 3-ton supply duct system. And so we always want to make sure and build our duct systems to provide 400 CFM per ton. And as you can see, the little flashing 400 CFM per ton reminder that this is what we want to make sure and design our duct systems for. So at 400 CFM per ton on a 3-ton unit, we're going to start out with 1200 CFM. 1200 CFM. Now, it should be noted, in all the following examples, we're going to size all of our main trunk components, at 700 feet a minute velocity. Now, that's right out of our velocity table on your handout. So 700 feet a minute velocity is where we're going to design our main trunk components. So starting out with our main trunk at 1200 CFM, if you refer to your duct calculator, and if we take 1200 CFM at 700 feet a minute velocity, we're going to find that with a 14-inch dimension on one side of that duct, if you refer to your duct calculator, you'll see that the other side of that dimension will be 19 inches. Now, let's face facts, team. If you're buying prefabricated duct, you may go to a 14 by 20. That would be perfectly acceptable. That would be well within the velocity requirements set forth in Manual D. If you're manufacturing your own duct, or if you're making your own ductwork, then a 14 by 19 would be no big deal to manufacture if you're making it anyway. So once we have our first section of trunk in place, we need to start finding out what our takeoffs or what our branch runs are going to need based on the CFM requirement in each space. Now remember, it's very, very important that we find out what CFM requirement we have in each space, in the conditioned space, before we build a duct system. And the best way to do that is to perform what is known as a manual J heat load calculation. And a manual J heat load calculation will set forth the exact number of CFM required in each space. So that's our recommendation as well. Perform a manual J heat load calculation, and that way you'll know how much CFM in each space. So we're presuming that you know, prior to building a duct system, that you know how much CFM will be required in each space, in each conditioned space. So with that in mind, let's go ahead and start building a duct system. So in our first space, we're going to find that we're going to have all of our branch runs at 600 feet a minute velocity. Again, that's right out of Manual D recommendations. So all of our main trunk will be at 700, and all of our branch runs will be at 600 feet a minute velocity. So in our very first space, we see we have 135 CFM requirement in our first space. And referring to your air duct calculator on that branch run at 600 feet per minute and 135 CFM requirement, if you'll line those numbers up on your duct calculator, you'll see that a 7-inch duct will be required. Now team, if you fall in between two different duct sizes, for instance, if you fall between a 7 and an 8, go to the 8-inch duct. If you fall between the 6 and the 7-inch duct, go ahead and go to the 7-inch duct, the larger size. Because we always recommend, as does Manual D, that you put a damper on each takeoff to balance or for final air balancing. So a slightly larger duct is better than having an undersized duct, and by all means you'll be able to balance that airflow anyway with that damper that you install. So we see in our first space we require 135 CFM with a 7-inch duct and a manual damper for final air balance. In our next space, we see we have 150 CFM, and again referring to our air duct calculator at 600 feet a minute velocity and 150 CFM, again we need a 7-inch duct with a damper. Finally, for our third takeoff on this main trunk, we have 145 CFM, and we see that we need a 7-inch duct for that as well with a damper. Now once we figure out how much air we've actually taken off, if you'll take your calculator and add 135, 150, and 145, you'll find that the remaining air in that next trunk line, if you will, has to be 770 CFM. Now we're going to transition down so that we can speed our air back up in our main trunk component to 700 feet a minute velocity. So referring to your duct calculator, we have 770 CFM left over. We then want to speed that back up with our transition to 700 feet a minute velocity for our main trunk velocity. So if you'll take 700 feet a minute velocity on your air duct calculator and find 770 CFM, and then refer down to the bottom part of the duct calculator, or if you have a duct calculator different than the one we're featuring in our program here, go to your duct calculator and find the corresponding rectangular duct size for 700 feet a minute velocity and 770 CFM. And so we've transitioned from a 14 by 19 on our main trunk down to a 14 by 13. At that point, we'll stretch out our next section of duct, which will be a 14 by 13 duct, and we'll go ahead and start doing takeoffs on that as well. So our first takeoff is 90 CFM, and when we refer to our air duct calculator, now remember our branch runs are going to be at 600 feet a minute velocity, 600 feet per minute velocity. So take 600 feet per minute velocity, line it up with 90 CFM requirement in this condition space, and we see we have about a 5.5 inch duct. So let's go ahead and round up to 6 inches, and with a damper, and we'll have good air balance in that space. Our next two takeoffs are the same. They're 125, and we see that we're right on the edge of 6-inch duct for 125 at 600 feet a minute velocity. So at this point in time, because we're just barely larger than a 6-inch duct, it would be acceptable to have a 6-inch duct on the 125 spaces where we have 125 CFM, or we could also round up or go up to the next size 7-inch if it was a construction constraint, or if you had a situation where you had a lot of 7-inch duct or whatnot, it would be fine to do that with a damper. But 6 inch is also acceptable. It's very close at 600 feet a minute velocity. So this time take 125 and 125 and 90 for this section of trunk. We take 125 and 125 and 90 and subtract it from 770 to see how much air we have left over in our main trunk. And in our example, we have 430 CFM left over. So at this point, we're going to transition from a 14 by 13 down to a duct that's going to be 13 by something to accommodate the 430 CFM. Now remember, team, the 430 CFM in that main trunk, we have to go back to our main trunk velocity of 700 feet a minute velocity. So referring to your air duct calculator, find 700 feet a minute velocity and 430 CFM, and we're looking for a duct size 13 by something. That is correct. So 13 by 8 will allow us to have 430 CFM in the remaining portion of our main trunk. So we then stretch that main trunk out, that 13 by 8, and at this point we have 430 CFM left over. We then do our final takeoffs, and each one of them is around 140 to 145 CFM. And referring to our air duct calculator for our branch runs at 600 feet per minute velocity and 145 to 140 CFM, we see we need 3 additional 7-inch runs at the end of that duct section to provide the CFM into the conditioned spaces. Now it should be noted, if you'll notice the last duct run, what we've done on our plan or on our duct layout here, we've actually backed up about 18 inches to 2 feet from the end of the duct. We capped it off and we took our last takeoff, that last 145 takeoff, about 1.5 to 2 feet from the end of the duct. The reason we do that is we do not want to depressurize the duct system. And so if we were to take a takeoff at the very, very end of that main trunk, it would actually have the tendency to depressurize the duct system. So what we do is we cap it off, and then we back up about 18 inches minimum. 2 to 2.5 feet is actually recommended. And so at this point, we see that we have built a supply trunk or supply duct for a typical 3-ton unit. This is actually considered a extended plenum duct system. Very, very efficient and quiet operation by building this duct system specifically on manual D velocity recommendations. The return trunk sizing is also very straightforward. Again, we're going to size our return trunk for 400 CFM per ton or 1200 CFM on a 3-ton unit. As we take a look at our velocity tables, we see that the recommended velocity for the return trunk is actually 600 feet per minute velocity is recommended. And so referring to the air duct calculator, let's find out what our trunk size should be. What is our trunk size for 1200 CFM at 600 feet a minute velocity, referring to the air duct calculator? Well, if we were using round duct size, we see that we're just a little, we're right in between 19 to 20 inch round duct, or a 15 by 20, that is correct. So our return trunk size will need to be based on a recommended velocity of 600 feet a minute velocity for our main trunk, our main return trunk going back, and that would be a 20-inch round or a 15 by 20 if you're manufacturing that ductwork. Okay, team, at this time, let's go ahead and talk a little bit about external static pressure. External static pressure is the total static pressure in inches of water column measured on the supply and return of a duct system. Now remember, the fan is designed to move air through the duct system by providing a positive pressure on the supply side and a negative pressure on the return side. Now to find external static pressure, the following steps must be taken. Step number 1, we need to measure the supply side air pressure. That will be a positive pressure. Then we'll measure the return side air pressure, a negative pressure. And then step number 3, we'll add the values together to determine external static pressure, also called total static pressure. So again, as a review, we're going to take the supply side static pressure. We'll then measure the return side static pressure. We'll then add those values together to find external static, also called total static. Now, the tools necessary to find static pressure are going to have to be a magnehelic gauge or a digital manometer. Basically, this gauge is designed to read fractional inches of water column. Now it should be noted a regular water manometer is not accurate enough for this measurement. So use a magnehelic gauge or a digital manometer that will read in fractional inches of water column. Now, if you're using the magnehelic gauge, you'll notice that when the gauge is at atmospheric pressure, it'll deflect this particular gauge at 0 if it's at atmospheric pressure. And then referencing to the high port, the needle will swing to the right as you observe it with a positive pressure. Likewise, with the gauge at atmospheric pressure and a negative pressure on the high port, it'll deflect the gauge to the left. So by looking at the positive and the negative pressure, or more specifically supply and return pressure, we can then add those values together, and in our example we see we have a 0.5 inches of static on the right hand gauge. We have a 0.2 inches of static pressure on the left hand gauge. Well, to find total static pressure, we add those values together, and in our example we have 0.7 inches of water column, external static, also called total static. So from this point on, team, I'm going to just talk about external static pressure. You'll know it's also known as total static pressure, but we will refer it from this point on to external static pressure like we see on our factory airflow charts. So this time, please refer to your furnace airflow chart, as we do some practice finding airflow or measuring airflow with our factory airflow charts. So in this example here on our furnace airflow chart, we're utilizing the chart for a TM9E type of furnace, or TM9E model numbers. So to utilize this chart, step number 1, you determine the model number off the chart. Next, you determine the speed tap on the motor. You then correlate on the chart, that model and speed tap with the external static pressure that you've measured. In our example is 0.5. You then drop down and cross-reference the chart to correlate with the model number and the speed tap. And in our example, we see we have 1150 CFM in this example. So from a practical standpoint, let's take a look at what we would do in the field. So in the field, we need to take supply static and return static. Now remember, team, on a furnace, the coil is not included, so you have to find a way to put a very, very small hole for your static pressure probe underneath the coil. Now please be careful that you don't drill into the drain pan or you don't drill into the coil. In addition, if you take the service panel off the furnace and temporarily remove the high temperature limits, you can use that as a convenient place to get airflow above the fan and underneath the coil. Or again, very carefully, just drill a hole on the underside of the coil cabinet without drilling into the drain pan for this measurement. Because remember, team, on a furnace, the coil is not included on the airflow chart. However, it is on an air handler. So with our first reading, we see that we have a TM9E80 furnace on medium high speed tap, and we have a static pressure on the supply side of a 0.3 inches of water column. So please write that down or make note of it. And then on the supply side, on the return side, we have a 0.5 inches static. So referring to your TM9E80B12 model number, medium high speed tap, we have a 0.3 and a 0.5 inches of static, which is equal to a 0.8 total. So referring to your airflow chart, we see that a 0.8 inches of static pressure, ESP, or external static pressure, 0.8 total, on that model number of furnace on that speed tap. Our CFM is 1097. Okay, let's do another one just to make sure everybody has this on furnaces. Our second example is a TM9E040 A12. It's on the high speed tap. So please find that on your furnace chart. We notice we have a 0.6 inches of water column, static pressure on the supply side. On the return side, we see we have a 0.95, so we have a very, very high static pressure. There's something going on with this furnace. We then add those values together on this TM9E40A12, and we see our ESP, our external static pressure, is 0.60 plus 0.95 is equal to 1.55 inches of static pressure. This is very, very high. Now, team, you'll also notice that of the numbers that we've reflected here, the 0.60 is on supply, the 0.95 is on return. And I like to take those separately for this very reason, because if you take them separately, you can kind of see what's going on with static pressure on each side of the fan. So in our example, we see we have a very, very high static pressure, 0.95 on the return. So the first place that I'd start to remediate this duct system would be on the return. So we have a total static pressure of 1.55. And referring to our chart, what is the CFM? Well, in our example, we see that the chart actually runs out at 660 CFM at the end of the chart. So we know we have less than 660 CFM in this second example. So at this point, again, we want to make sure and find out why we're having this problem. We may have some return air duct that's collapsed, or maybe we have a filthy filter. So always remember to change the filter and clean the evaporator before doing any of these static pressure checks. That's just good practice. And make sure you don't have any obstructions or you don't have any zone dampers closed or anything like that when you're doing your static pressure checks. Okay, at this time, let's go ahead and roll into airflow and duct design for module number 4. And module number 4 is going to constitute using factory airflow charts and finding ESP, or external static pressure, for air handler products. In addition, we'll also talk about finding airflow using what's known as the temperature rise method of airflow measurement. So referring to our air handler charts, now you're going to notice in your handout package, you're going to have two air handler charts. You're going to have an AHR air handler model chart, and you're also going to have an AE air handler model chart. Well, these charts work very, very similar, like they did with the furnace charts, and the fact that step number 1, we're going to determine the model number. Now please note, on air handlers, you may also have a voltage table as well. So if it's applicable, in other words, on the AHR air handler chart, you'll notice you have a 208 volt and a 230 volt table. So be sure you're looking at the right table on an air handler. So again, step number 1, we find the model number. Step number 2, we determine the voltage if it's applicable for the appropriate table. Step number 3, we determine the speed tap just like we did before. We then correlate that to the static pressure that we measure, and then we find the CFM like we did on our previous examples with our furnaces. Very, very similar on the air handler. So let's do a few examples together as we talk about measuring airflow on air handlers, and then we'll also learn about the temperature rise method of airflow measurement as we start winding down the training for this session. Okay, so referring to your AHR air handler model chart, let's find an AHR 30B, an AHR 30B air handler, and we're on medium speed tap. Now please note, team, this is on the 208 volt table, so make sure you're looking at the 208 volt table. An AHR 30B, medium speed tap, 208 volt table. Our first reading on the supply side is actually going to be 0.3 inches of water column. Now please note something, we don't have to try to sneak underneath a coil like we did on a furnace. And write this down, or please remember it. On an air handler, the coil's included on the airflow chart. So all you have to do with an air handler is just poke a hole in the supply plenum and poke a hole in the return plenum so that you're reading static pressure for the fan. So our first reading is 0.3. Our supply reading is 0.2. So then we add those two values together, a 0.3 plus a 0.2 inches of static, and we find that our external static pressure, or total static pressure, is 0.3 plus 0.2 is equal to 0.5 inches of static. Now, please refer to your AHR 30B air handler chart. Don't forget you're on the 208 volt table. And at 0.5 inches of static, what is the CFM we're seeing on this AHR 30B air handler? Medium speed tap. 0.5 inches of static. You should find 890 CFM. Okay, let's do a couple more examples, but now let's go to the AE air handler chart. The AE air handler chart. The first one we'll look at is an AE air handler model number 18B. And 18B, this is a 1.5 ton air handler. We are on the high speed tap number 5. And on our supply side, we see that our supply static pressure is 0.30. 0.30 on the supply side. And we see that we have a 0.2 on the return side. So 0.3 on supply, 0.2 on return. We then add those values together for a total of 0.5 inches of static pressure. 0.3 plus 0.2 equals 0.5. Now please refer to your AE18B model number on your air handler chart. High speed tap, 0.5 inches of static. What is our CFM? Good job, that is correct, 1023 according to our chart. So this is the amount of CFM that's actually moving through that cabinet under these points of measurement. Let's do one more. Let's take an AE36C air handler. So you're on your AE air handler chart. An AE36C, high speed tap number 5. Our supply side static pressure is 0.6. The return side static pressure is 0.2. We then add 0.6 and 0.2 to get our total static, also known as our external static, our ESP external static of 0.8. So please refer to your AE36 air handler on your AE model chart. High speed tap number 5, 0.8 inches of external static pressure. What is our CFM? Yes, now we see that at 0.8 inches of static pressure, we're actually at the end of the chart. And the very end of that chart is 1348 CFM, so we know it's less than 1348 CFM because that's where the chart runs out. So this is important. As we take a look at our numbers, we see that we have a very, very high static pressure on the supply side, 0.6, and a fairly normal static pressure on the return side, 0.2. So in this particular example, we could use these numbers to help remediate or figure out where our problem is on the supply. So we see that we have a high static pressure on supply, so we'd start looking at the supply duct to make sure it's not collapsed. Or we want to make sure that we don't have zone dampers that are closed, or we don't have registers that are closed, that the homeowner is closed for whatever reason, and because that'll drive your static pressure up and your system capacity and your system efficiency down. So be sure that we always stress that we have to have proper airflow for proper system capacity and humidity control and ultimate comfort. So at this time, we're going to do one other method of airflow measurement. This is an old method, and all it requires is a good quality volt ohm meter and a amp clamp on the electrical side and a temperature probe. This is called the temperature rise method. So the temperature rise method says this: CFM is equal to the output of the device in BTUs divided by 1.08 times delta T. Now that delta T, or that triangle T, is the temperature difference between supply and return air. And by the way, team, all of these formulas are on your formula page as part of your handout package. So, step number 1, we're going to energize the heat strips on an air handler or an electric furnace and make certain that the outdoor unit is shut off. We're going to multiply the measured volts times the amps, and then we'll multiply that result by the mathematical constant of 3.414 to find BTU output. So that volts times amps times 3.414 is how you find the output of an electrical device and convert it to BTUs. Step number 3, we're going to measure the supply and return air temperature within 3 feet of the air handler and find the difference. That's the delta T portion of the formula. We then multiply that number by 1.08 and find the sum. Finally, we divide the output in BTUs by the result of step number 3 to find our CFM. So let's do an example together. Please clear your calculator as we do this example together. And again, this is on your formula page to help remind you after our training today. So let's say we have a 2-ton unit and we want to confirm that we have 800 or close to 800 CFM on our 2-ton unit. So we're going to, step number 1, we're going to measure the voltage and the amperage and multiply times 3.414 to find the output. So please take on your calculator, your voltage is 249 times amps, 33.6, times 3.414, and that number will give you the output of that electric heat strip and that air handler without the outdoor unit running. So it should be 28,563 is the result. Please write that down or remember it and put it to the side so that we can have that number convenient when we do our next steps. Our next step is we take our supply air temperature and our return air temperature and we find the difference between those temperatures. So on your calculator, take 105 minus 72. That equals 33. That's the delta T portion of the formula, 33. And then take 33 times 1.08 to get a number. So 33 times 1.08 equals 35.6. We then take 35.6 and divide it into that larger number, that output number that we had before, 28,500 and change. And we find that our CFM is 802. So that's the temperature rise method, team. It works very, very well. It's a quick, easy way to find the airflow on a unit that's already been installed. You go right to the unit, you energize the heat strip, and you select the airflow or the fan speed that you're testing. Energize the heat strip, make sure the outdoor unit's off. Measure your volts times your amps, multiply times 3.414. That'll give you some number. That's the output number of the formula. We then take the temperature difference of the supply and the return, and we find the difference. Multiply that difference times 1.08. That will give you some number that we divide into the output number, and that will give you your CFM. It's a very, very easy, fast way to measure CFM. It's extremely accurate. It will get you within about 5% or less of a flow hood, and so it's a good way to confirm airflow on a system that's already been installed with all the components in place. So at this point, team, if we were a live session, we would go ahead and entertain your questions at this time. But this is a recorded session. So we'd like to thank you. Thank you for listening to thank you for attending and listening to our recorded session today. And by all means, if you have any questions on the recording, please contact me or our technical support team, and we look forward to training with you again. Thank you very much and have a great day.